Alright, let's do it. Alright, so today I already made the code for today, but I'll run the program. But we're gonna be talking about encoders and IMUs and how we can use those for chassis navigation. And then also we'll talk about PID loops at the end. I don't have code for that, but I have a slideshow with theory and stuff that I will share to you guys. Very cool. All right, let's make a new class. Um, let's add our @autonomous tag. I think we need that. And then after public class, remember, every time we need to extend by linear op mode. There we go. Click this, implement methods, so run op mode, and perfect. All right, I'm gonna copy over our motor things because if we do it each time, it just becomes kind of annoying to type all that out. And we're going to add a new sensor that we need to initialize as well, called the IMU, which stands for Internal Measurement Unit. And on your robot, that's going to be on, it's probably already pre-configured on port 0 of the control hub. So if you go into your driver station, connect to your control hub and go into configuration, check port 0 of the I2C, and it shall already be configured as an IMU there. So don't plug any motors into that one. All right, copy over our hardware inside of our public void run op mode. Also, all of this code, this file is already posted on GitHub, by the way. Okay, so the first thing we're going to be doing is making a run to position program with our motor encoders. So we need to first stop and reset encoders. So each motor has a built-in encoder in that measures internal rotations of the motor, and there's a wire on it, and you can plug it into like the spot right next to where the motors go, and that's how you can get data for each motor. We personally don't use motor encoders because a rotation, or what is called like ticks, is the measurement they use for rotations of the motor. That doesn't necessarily correspond to actual robot movement. So it's actually better to use dead wheel encoders, which we're using rev through bores right now, and they're connected to an omnidirectional wheel on the X and Y axis. And that way, once this wheel moves, this wheel only moves if your robot actually moves. So the dead wheel encoder only increments if your robot increment or moves, which is pretty helpful. But we do use motor encoders for like linear slides and stuff and sub-assemblies, just not for the chassis. Okay, so the first thing we're going to be doing is setting the mode to stop and reset encoder. That's going to make all of our encoder values 0 right off the bat. Next, we need our wait for start. Then anything after this is going to be run. right? And the first thing we need to do is set a target position. So if you click dot set target position, then here is where you include your encoder ticks that you want it to run to. So a good practice is measuring out how many inches or how many ticks per encoder or inch, encoder ticks per inch, yeah. And then that way you can find out like how many inches or how many ticks it takes to go like uh, a number of inches, say like 5 inches, then you can determine that pretty easily. So here, let's do 1000. And we're going to need to set this for each motor. Okay, perfect. So now to get them running, what set target position does is it kind of does all the work for you. It has like a deceleration function in there. As you saw, that was in the when I ran the program the first time. That was the first movement it did was a set target position. So now we need to set the mode to run to position. So that's going to be your set mode, and then just start typing all caps run to position. I'm actually just going to copy these over. Also, if you have any questions or if you think I'm going too fast, then let me know in the chat or something, or you can just speak up. Okay, now we need to get our motor running. So let's give all of our motors a power to start off with. Oh wait, actually, let's just copy over our drive function that we made last time so that we don't have to type out everything again. Remember, this goes outside the run-off mode and it goes inside the week 3 class. So let's set drive equal to 1. That gets the motors running. Now we need a while loop. And we can just use one of the motors since they're all going in the same direction. We can just use like the back left motor, say, and we're going to need dot is busy. So if the motor is working towards the target position, is busy is going to be true, but if it's at that target position, then it's going to be false or within tolerance or something. Which reminds me, I think that, oh, but I think in one of the DC motor classes, it might be DC motor X. I'm just going to show this as an example. Let's set motor equal to, this doesn't this doesn't exist on the virtual robot, so, but you can just use the DC motor X class for any DC motor. So if you wanted to make like front left or front right at DC motor X, you can do that. I'm just gonna, so it doesn't throw errors. Okay. So it has a lot more methods. It has a built-in PID function. it has a get velocity function using the encoders, and it also has get target position tolerance. And you can set your target position tolerance as well. And you can also set your velocity too, which makes it, in my opinion, a lot more powerful than the simple DC motor class. So I think our target position tolerance for these simple DC motors is 6, but if we want it to be bigger or smaller, then we can do that as well. But that's just an example. All right, we can delete these so they don't throw errors. All right, so we don't need to do anything because it's already the motor power is already like set and the motors are just going to be running on their own. So we can just write continue and it'll just loop through this. And then after that, we need to set our motor powers all to 0. Nope, what did I do? I forgot to put the reverses in. Whoops. Cool. Oh yeah, telemetry. So if you want to debug a problem or something, you can use telemetry, add data, and your first argument is going to be caption. So let's just say encoder value, so space there, comma. Your second one is going to be the value that's showing. Back left dot get current position. And then we always need to update our telemetry as well. So as you can see, it stopped at like 994 or something, which is 6 away from our target position. So I think the target tolerance is 6. But you can change that if you use the DC motor X class. And you can also change the PID coefficients and stuff. But if you want more control over it, like if you weren't running the dot target position and say you wanted like tolerance of 1 tick or something, then you want it to be faster as well, then you're going to want to use you're just not going to want to use the run to position mode. So let's set, so let me just copy these over. I'll put a sleep in here. And you're actually going to use run without encoder, because if you use run with encoder, then it's actually slower on the real robot for some reason. But without encoder still allows you access to encoder values. All right, so here we're going to get int target, let's say 3000. We're going to create a while loop again, of course. While back left, we can say dot get current position is less than 3000, then drive with a power of 1. Then once it finishes, then stop all the motors. Oh, wait, hold up. It'll still work, but okay, cool. So with this, though, it tends to overshoot the target because you're going at full power until it's not less than the target anymore. So in a real robot that has inertia, once you set the power to 0, it's not going to stop on a dime right away. It's going to just continue going for like maybe even a couple of inches, which can throw your program off, which is why you need acceleration and deceleration. And some softwares like Roadrunner, if your team is going to use Roadrunner, already have that built in. But in some cases, you'll need to build that in yourself. And we can talk about what that looks like at the end of the class today. But now we have IMUs to cover. Okay, so let's configure our IMU with this piece of code right here. The device name is just going to be IMU. And let's make a turn function as well. And for this, our left side wheels are going to have to be at a opposite from our right side wheels. So let's put negative power and negative power here. Okay, let me look at what I did for this. Oh yeah. So we need to get our heading from the IMU, which is called get robot orientation. And we're going to need, if you hover over it, it tells you what like parameters you need to include in there. So you're going to need an axis reference, axis order, and an angle unit. So I think we use intrinsic. Yes, intrinsic. Going to need axis order. I like to do X, Y, Z. It doesn't really matter. And then angle unit. So let's use degrees. Okay. And then we're going to use third. Nope, third angle because our Z heading is the one that's our lateral heading based on how you put the control hub. So if the control hub is like on the wall of your robot, like it's perpendicular to the ground, then I think it's going to be you need to use Y to find the lateral heading. But if it's parallel to the ground, then you use Z. It's also going to return some weird like angle stuff that I really like, and it makes it harder to work with. So it starts at 0, and if you turn clockwise, it increases till 180. But once you go past 180, it turns into negative 179, and then it increases until it reaches 0, which makes it kind of hard to work with. So we're going to need to normalize our values. Oh, so I'm just going to take this function and copy and paste it because, okay, let's walk through what this does. IMU normalize, it takes in an angle and it says if this angle is less than 0, then let's add 360 to it. So If we're at an angle of -1, that's less than 0, then we add 360, then that's 359. If we're at an angle of -90, then it's 270. -179, that's what, 181. So it normalizes it as if you're facing forward, 0, and it goes from 0 clockwise to 360, which makes it a little easier to work with, in my opinion. So let's pass this angle into our IMU normalized function. I hate the zoom thing. Okay. Or before we do anything, I do want to see what the angles are giving me, like which way is positive, which way is negative. So I'm just gonna make a timer real quick. While this timer, whoops, while the timer dot seconds is less than 3, then let's just turn at 0.4 power. Um, let's get our heading value in here. After this, it's set to 0. And let's take telemetry, add data, heading, heading, and update this. Perfect. Okay, hopefully that works. Okay, so clockwise decreases our angle if we start at 360. And with the positive power, we're turning clockwise. All right, so let's set a heading target of um 270. Yeah, while heading is greater than 270, then we continue to turn. Okay, but it's not going to do that because it starts at 0. The initial heading is 0. So our heading is never actually going to be greater than 270. So we need to start turning first of all. Or, hold on. Well, heading is greater than 270, or heading is equal is equal to 0, then we can run the while loop. And that does the same thing as turning beforehand. Nope, I'm wrong. Okay, what's going on? Okay, this will be a lesson in debugging. So first, we want to see what the heading is going into the function. So I'm going to remove this. Let's get our heading and let's sleep here. And let's take out the turn as well. Let's make this like 2000. Okay, so our heading is actually a really small decimal value. That's fun. So let me think. What we can do is if heading is less than 10, then we can turn. Let me take the sleep out. There we go. Okay. So as you can see, it's not exactly 270. It's a little bit greater than 270 because there is like a little bit of motor inertia. There's also the fact that um, the program isn't incredibly fast or anything, so it doesn't run the while loop iterations fast enough to stop the program exactly when the heading is 270. But I think that's all I had in the code. So let's talk about how we can fix that real quick. And we can do that with the PID controller, which is the proportional integral derivative controller, which are some familiar terms if you've taken calculus before. But if you haven't taken calculus, you don't need to worry because I'll explain everything. It's not that dependent on calculus, actually. So, yeah, we don't use time-based controller, too many external factors that can decide the final output of the system, yada, yada, yada. It's a closed loop control feedback system is what PID is, and it gives you deceleration, basically. We also don't use run to position because it's less accurate. Okay, so the PID controller works with like this. You take your error, which is your target state, minus your current state, and multiply that by a tuned constant of proportionality and add a constant of integration times the integral of error. So error multiplied by time, and then add that to a constant of derivation times the derivative of error, which is error over time or divided by time. So let's talk about the proportional output. Of course, like I said, your error is going to be your target minus your encoder value. Sorry. KP, which is your constant of proportionality, is a tune variable, and your output is these two times each other. For your integral output, you're going to find error the same way, but you're going to find cycle time, and this is also going to be helpful for your derivative things. You can use those for both. Um, and the integral is error times your cycle time. And you multiply that by your tune constant integration to find your integral output. And for derivative, you take your error and you divide it by your cycle time and multiply that by a tuned constant of derivation. So integral output is for times when your proportional output can't get you far enough to the your desired state. So let's say you're running your chassis and you want it to reach like 2000 ticks, but you're only using the proportional output. You're not going to get to 2000 ticks perfectly because your robot at some point the power value, the output of this is going to be so small that your robot just won't be able to it just doesn't have enough power to move the robot anymore, the output of this. So that's why you add the integral output over there. It takes the error multiplied by time and it gets rid of what we call steady state error. And your derivative output, it measures how the error changes over time. So if your error is getting smaller faster, then your derivative output is going to be also smaller. And if you tune that to be a larger part of your um, PID control algorithm, then it's going to be way more responsive to how your error is going to change in the future, which might not make sense. But if you want like a more in-depth explanation, there's some links on here. Yeah, that kind of explain it better than I do. I think they actually have some code in here. Yeah, but try not to get fooled by these calculus things. This is an integral sign right here. Just means um, function et error multiplied by change in time. So that's just what I was talking about. I'll share this slideshow with you. It also at the beginning has stuff about threads, which I guess we can go over now because I have time and I don't really know what else to do. So your teleop and autonomous are going to be synchronous programs. So you can only really run one motor or like subassembly sort of like thing at the same time. So you can you can use multi-threading. So you can use multiple things at once. And the way this works is you have a control hub CPU with multiple cores, and each core has multiple threads on it. I think the control hub cores allow you 2 threads per core, and it's a 4-core CPU, so you can run 8 threads at a time. Wait, this is a really cool video. I actually really like this. This is from a couple years ago, but it's a demonstration of threads on our robot. As you can see, I'll play it again. The turntable, linear slides, and arm all went up at the same time, which is really helpful because we are already locked and loaded as we get to the pole. We don't need to like wait or anything, which makes it like really fast. So we're going to create a new thread. Okay, let me just show it in the code. Oh, never mind. I don't have functions that we can do that with. but we create a new thread by saying new thread, and then this is going to be a lambda definition. So you can pass a function as a parameter into another function. Or so creating a new thread is going to create a thread object, right? And we can pass the function to open the claw into that, and then just by this function declaration here. And then after the thread, like after we close this first parentheses, we're going to use dot start to run the thread. And once it completes everything in the thread, it's going to kill it automatically. And if it doesn't kill it automatically and it keeps running, then you're going to get a memory leak, and you don't want that. The second way you can do it is a class method, and you're going to create another class, and you're going to extend the thread class, and you're going to use the public void run method. And whenever you call it in your main run op mode thing section, you would use the dot start method as well. And yeah, memory leak when a program keeps objects in the memory heap that aren't being used. Okay. Um, so that's how you can get a deceleration onto your chassis and subassembly movements. But if you want your robot to, or like, yeah, if you want your robot to accelerate, which is pretty beneficial because if you just set your subassemblies or motors to like a max power right away, then there's going to be slipping because you can't just get like there has to be acceleration. You can't get anything from at rest to full velocity in an instantaneously. That's just not possible. So one way you can do this is by finding out your max velocity of whatever you're using, which is you're just going to run your motor as fast as you can, and you are going to get the encoder ticks and take it and divide that by time so you can find encoder ticks over time, and that's your max velocity. And your maximum acceleration is going to be the time it takes for you to get to that max velocity, which you can also write a program for. Um, maybe let me see what we're doing next week. Okay, so next week is the class over mechanism wheels, so that's important. I'm not going to talk about motion profiling there, but I think I have a slideshow for motion profiling that I can share. There we go. Okay, yeah. So the problem with our PID controllers is they start off with a very high output because of the proportional and integral, or no, just the proportional part. So we can't just get into maximum velocity right away. The motor will slip. So we need a way to accelerate into top speed, which requires a motion profile. So these are the motion profiles used by Roadrunner. Velocity over time is trapezoid, and acceleration over time is this like ladder looking function. Um, if you guys are taking AP Physics 1, the very first thing you learn is kinematics equations, which you can use to find the time it takes to the time and distance of your acceleration part, the time and distance of your deceleration part, and the time and distance of your cruise part. And then using that, you can build a motion profile for if say if you want your robot to move forward 10 inches, you can create a motion profile function and you feed 10 inches into there and it'll create a motion profile automatically for you. Where what you do is the robot reads the time off of like a elapsed time function or whatever, and it uses a PID controller for velocity to tell the robot like what it needs to do. So if it needs to accelerate, then it'll have a higher proportional output because it's accelerating. But yeah, that's motion profiles. I think I have a motion profile function in GitHub. Hopefully I do that I can show because I feel like what I'm saying is not making sense right now. Yes. All right. Let's take our velocity one. So we have inches, ticks per second squared, and double time. So ticks per second is your maximum velocity, ticks per second squared is your maximum acceleration, and your time is the elapsed time. It's your timer that you're using in the PID function. So you find the distance by taking your inches and dividing that by your ticks to inch multiplier. Then you find your acceleration time by dividing maximum velocity by maximum acceleration. You find your halfway distance by dividing your distance by 2. And we need to find if our robot can even make it to our halfway distance with its maximum acceleration. So we find that distance by multiplying 0.5 times maximum velocity times our acceleration time squared. And this all comes from kinematics equations. Yeah, it comes from from this one over here mainly. Okay. Yeah, and we take our time, we have trajectory times and all that, and we return what the velocity needs to be at a certain time. And we have a PID function. No, we don't. Never mind. Well, you're supposed to have a PID function.